Well, there's the title of my talk, and I think the first thing I would like to do is to thank the organising committee for this follow-up meeting. It certainly brings back some very happy memories of 2011. And I'm going to start, first of all, just by saying this is joint work with an honours student of ours, Hassan Sadiq, who came into my office and expressed interest in a project on design for his honours project module. He then went away, came back some months later with this beautifully done project. And so he and I were able to interact after that, cross-check results, and that's why it was joint work. I actually should start off as well with a couple of apologies. I couldn't think of a better word for it. There was a great deal of work went into this, lots of simulations, lots of table productions and so on. And I haven't spoken about it before. Hassan has spoken a couple of times on the topic, and I realized as I was preparing the talk that it could all be reduced to a big question and 3 graphs. However, I'm going to linger a little longer, and the second apology relates to the fact that I wasn't quite sure of the audience, and so for certain people this introduction to the problem will be overly familiar, but hopefully for others it might not be. So let's start at the beginning and just say there's a special thanks here, firstly to Bill Rosenberger and secondly to Nancy. Why? Well, because when we were at the Institute in 2011, they recruited me into a project that they were busy with. And at the end of all this, I was the simulation queen in this whole operation. And at the end of it all, I had a question. And it was this very question of startup designs. There's a rather bizarre thanks that I had to throw in, and this is the reviewers in Stats in Medicine, because it's now accepted and available online. And some of my colleagues back in Cape Town will affirm to the fact that once in a while they would hear me saying, "Oh no, not again," and a week later saying, "Oh, of course they are right." And it did a huge amount to actually improve the project and the paper. So if the reviewer is lurking here, then thank you very much. It really was greatly appreciated. So let me start off with the problem, and we're looking at a clinical trial, 2 treatments, A and B, binary responses, in other words, yes or no, success or failure, and patients are coming in sequentially, and they're assigned obviously to either treatment A or treatment B, and the response is known almost immediately. So in other words, either they fall over or they don't. The objectives of the design, again, this might be very familiar to many, but it's worth throwing in just before we start. Perhaps one of the big things is this is response-adaptive, and so one must take advantage of that. There is always the classical problem of ethics versus efficiency. The patients will tell you they want to be on the best treatment. The statistician will tell you that they want to be suitably efficient in recording the differences between A and B, and the doctors will probably say, "I don't know, I want my patients on the best treatments, but I also want to know how much better, say, treatment A is than treatment B." In terms of efficiency, I've popped those in. Efficiency in estimation, efficiency in power. There are some other interesting issues that do creep in. The first is what's called selection bias, which could happen. People might start to guess what order is going on in the clinical trial. And the other one is accidental bias. Again, that's simply conditions are changing. One day it's hot, one day it's cold, something we can't control. And finally, of course, there is a cost problem involved. So that's just a very broad overview of the thoughts that go through one's mind when one thinks about response-adaptive designs. Two basic types of response-adaptive designs. I've termed the one non-parametric, and I think the prime template there is probably the earn model, randomize play the winner, drop the loser, and so on. Very simply, and I wouldn't normally say this, but just to highlight where I'm going, randomize play the winner, you grab a convenient earn, you put an A ball in and a B ball in. When the patient comes along, you take out, say, A, you tell them to have treatment A, and you put it back. If it's a success, you add another one, another A. If it isn't a success, you don't do anything. So you'll see in a moment why I wanted to highlight that, because the second type of design is parameter driven, and there's been a great deal of work on this. There's a name and target. This is my favorite because I have a horror of forgetting what RSIHR stands for. It stands for Rosenberger, Stallard, Ivanova, Harper, and Ricks. I hope I've got it right. And so they named the procedure. That is, of course, an acronym for their surnames. Another one is E-RAID. I think perhaps labeled because these wonderful acronyms were creeping in. This is just an efficient randomized design, and so on. So this is all beautifully worked out and reviewed in Hugh and Rosenberger. Lots of wonderful mathematics as well, but lots of down-to-earth explanations of what's going on. My focus is going to be on parameter-driven, and let me just quickly set the scene. If we have N trials, NA patients on A with SA successes, NB on B with SB successes, we're simply going to estimate the probability of a success with A, PA hat, and the probability of a success with B. And then we're going to allocate the next patient using those estimates. And I've just put in here the allocation probability that was worked out by, wait for it, RSIHR, got it. And this was one where they fixed the sample size, and they were looking at the numbers of, they were trying to minimize the number of failures. So where is the problem? Why was I all so excited after the collaboration with Bill and Nancy with a particular feature? And the feature is this, that in order to get those estimates, you need to start the whole thing off. The earn models are self-starting, as that's why I spent a wee bit of time sort of explaining what can we do as a startup procedure. To my amazement, and I checked with the experts, there seems to be no regulatory documentation. So what I'm trying to say is a huge amount of work has gone into developing these parameter-driven designs, but how do you start them up? There are murmurs in the literature. Hugh and Rosenberger have an odd line or two, and Alessandra and Sandra also, and I can't say the last name, so I'm going to rapidly avoid it. And then we ourselves, in our paper that came out in 2013, again, we used a particular, it was simulation based, and so we had a sort of startup procedure of complete randomization until we could estimate the parameters sensibly. There's a very attractive paper come out by Zhu and Yin in 2014, that's in JRSSC, or Applied Stats as we know it, and they have a likelihood ratio test which they keep on feeding results into until it becomes satisfactory, and then they go on to the response-adaptive section. What's the default? What are we going to do? Let me just now sort of identify the different approaches, the one that I was happy with was run until meaningful estimates. In other words, until the probability of success of A is no longer 0 or 1, and likewise for B. And this is where the reviewers put me on my toes, because there are other ways of approaching this. We could say we are only going to allow 10 patients onto the trial, and if you happen to have P hat A is 0, just adjust it somehow, and then start the randomization, the response-adaptive design. A final one, and Bill assures me that this is not Bayesian. Let's just assume that the probability of success for each treatment is 1/2, and let's just get on with it. So those were the possible approaches, and now I actually come to the present study, and I'll just explain how we set our scenario up and what we did. So the strategy was a preliminary run. It wasn't looking at fixed numbers, and it wasn't looking at probability of A, probability of B is 1/2. We were looking for meaningful parameter estimates, and so obviously P hat A must lie greater than 0, less than 1, likewise for B. And so the stopping conditions were this, that we must have the number of successes of A greater than 0, less than the total number of people assigned to A, and likewise for B. That was the strategy we adopted. The designs, there was a whole host of designs, and I'm not going to report by any means all of them. I'll just go through these quickly. There is the systematic design, give them A, give them B, give them A, give them B. Horrible selection bias, of course, because after a while you can predict that. There's this wonderful design or plan that appears in Efron's seminal paper on the bias coin design, and he mentions student sandwich plan. Lovely phrase, which is A, 2 Bs, 2 As, 2 Bs, 2 As, and so on. I couldn't find any further reference to it, but I thought it was so appealing that we had a look at it. And then I conjured up this thought, why not give everybody A until we get a meaningful estimate, and then give everybody B? Horrible selection bias, and I'm not going to focus specifically on any of those. Let's look at some randomized designs. And the complete randomization was the one that Flournoy, Haynes, and Rosenberger implemented. It's the attractive and obvious one really to look at. And I've starred the designs that I'm going to use for the 3 graphs that tell the story. So this is star CR for complete randomization. I still rather like the thought of one at a time, and so I said let's try a randomized one at a time design. Complete randomization, this isn't phrased as precisely as it could be. Complete randomization until A satisfies our criterion, and then carry on with B, which hasn't already satisfied the criterion. Alternatively, let's say that B is satisfied first, so we wait for that to happen, and then we carry on with A. And that's got a special star as well, because I'm going to talk about it. We didn't stop there. There's more designs. Permuted blocks. There's a typical permuted blocks in blocks of size 4. You randomize within each block, and then you carry on. And it avoids the dreaded selection bias, but nevertheless there's something slightly systematic, but not terribly systematic. That's one of my starred designs as well. We also looked at block sizes of 10. Efron's biased coin design, I didn't look at in any, well, we looked at, I'm not going to discuss it now. The point of missing some of these designs out is that they performed very similarly to others, especially the starred designs. And then I thought we may as well pop in an EARN model. I did explain how you pick a treatment out, and if it's successful you put an extra ball in the urn, and of course they are going to be very strongly biased towards the better treatment. And for this, the randomized play, the winner, was quite dramatically in favour. Drop the Loser was kind of cute, so I've kept that in what's going to follow. So what are the priorities? Going right the way back to when I highlighted what are the sort of desiderata of a response-adaptive design. In this case, I felt the one and only requisite would be to have a small number of trials. We have a total of small n, and we stop when the two conditions for meaningful estimates happen. End of story. Along came stats in medicine and reminded me very nicely of thinking about a few other things, particularly the ethics, so that the proportion on the better treatment, NA over N stop, was examined, and to think of an efficiency metric. You'll see that the text has got smaller and smaller because I felt there was less and less importance. I did argue that the efficiency metric, you're not really looking for efficiency in your first block, you're waiting for your response-adaptive design, but nevertheless we recorded that. And then finally, in teeny tiny writing, there was selection bias, which I didn't particularly handle. So here comes, I've given you the big question, which is how do we start these parameter-driven trials off? Here comes the graphs. Okay, I use only the starred designs. We had the this is where all this great work appeared. PA and PB going from 0.1 to 0.9, assuming that A was better than B, and then the calculations. And in a way, the reason I ever embarked on this was I had a sneaky suspicion that one could derive a lot of fun out of some exact calculations, particularly on complete randomization and so on. It all finished up with the grand simulation. N stop, well, let me just show you very quickly, and this sort of first of all, a little rider to exact designs, and secondly, something that's kind of important for the interpretation of the graphs that follow. So I've only got one treatment. These could be the building blocks for writing out elementary sort of probabilities relating to things like complete randomization. Very straightforward sort of stuff, but always fun to handle. So the probability of stopping, it's kind of obvious. You wait, you have either n-1 failures and then a success, or you have n-1 successes and then a failure. Why am I telling you this? It should be obvious. Here's the other lovely building block. And so surely we could put all those together, which we did. The probability statements were reasonably nice, and then I pressed the button for Mathematica to calculate the means, and I got several lines of result out. So in a way, unfortunately, the dream of exact calculations fell away. In any case, fiddling with efficiency would have been awkward. I'm now going to show you something else that's obvious, but it's important not to be distracted when the three graphs appear. And it's simply this, that very obviously, if your probability of success and failure, if either or both are close to 0.5, you're going to get to the required conditions pretty quickly. If, for example, the probability of success is very high, just say for the one treatment, you're going to go on for a long, long time before you pick up that failure. So the point of this slide really was just to look at our building blocks and give you a precursor of what's to follow. Here come the graphs. This is a preliminary graph. It's not graph 1, 2, or 3. The reason for showing you that rather elementary curve is this, that these plots of the expected value of n stop against PA, PB, you can see at the bottom there, I'm not sure, no, at the bottom there I've got PA, PB. Remember, PA is always better than PB, so you have the rather strange increments building up. But the point of the slide is, if the probability of A is 0.7, the probability of a success with B is 0.6, you're going to get to to your stopping criteria pretty quickly. In the extreme, if it's 0.9 and 0.1, you're going to wait an awful long time for both of those stopping criteria to kick in. And so here come the graphs. All three, well, this is the first one. And I put the previous slide in so we don't get too distracted with the shape of these things. And as you can see from that, my favorite design performed beautifully. This is the complete randomization until one of the conditions is satisfied and then run with the other. I've put in the blocks and I've also popped in complete randomization. A little reflection would probably tell one that the CRD design is necessarily going to be the best in terms of the expected value of n stop, but it's nice to see it happening. Here comes graph, oh sorry, no, this is just an extra graph, just to highlight what happens with an earn model. Drop the loser. It goes sky high when the probability, say, of A is 0.9, because you're going to so much favor that treatment, it's just going to accentuate it on and on. Anyway, that was graph 1A. Here comes graph 2, and this was where I had a silent thank you to the reviewers, because my favorite design that I was living with did not perform very nicely. The straight line that you see there is just 0.5, the expected number allocated to A over the number of trials we had until we stopped. The blocks necessarily sit happily there. Drop the loser favors treatment A all the time, and it just gets worse if the probability of a success with A is very, very high. But what about poor old CRD? Why did it fail me? A little reflection can tell us why. Because if I look at probabilities when it's dropping badly on the left-hand side, it means that the probability of A is bigger than the probability of B, and it's closer to 0.5. So I get to A pretty quickly, so that condition is satisfied, and then I bring in B and run it, but the probability of getting B is less than A, and it goes on and on. And so, in a sense, that was the disappointment. If the probabilities of success for the two, A and B, are less than 0.5, we are really going to have trouble persuading anybody to use a procedure where the probability, where the number of people on the worst treatment are getting is high, and ethically that's bad. Here comes the last graph, graph 3, and there's nothing really intuitive to say about this, except that my favorite design didn't do awfully well, but it tried hard. And I put the blocks in as well. And again, I should just reiterate that the blocks design and the completely randomized design were very nicely representative of certain other designs. So at the end of it all, what is the conclusions? I went to a wonderful sort of discussion which involved, I like these little discussions, these little what's the word? Little trails away from the main theme, for want of a better word. Okay. I went to a wonderful discussion involving one of South Africa's premier forensic scientists and one of their leading judges of the High Court. And they were discussing the fact that forensic evidence is not as clear-cut as we all try to imagine. We always think if the DNA evidence is there, that's great, that's it, it's finished. It isn't like that. And so at the end of this discussion, and the judge agreed with all this, they said to him, they asked him the key question, well, what would you do if you had a bit of DNA here and a bit of something somewhere else and an odd fingerprint somewhere else? And he said, I would look at the tapestry of evidence. And I'm just very, very fond of that phrase. Why? Because in many ways, that's what these clinical trials are all about. We do have, and I had here, a tapestry of evidence. We've got number of trials, we have number on the better treatment, or proportion on the better treatment, and we also had a bit of efficiency thrown in. So just going through things quite quickly, randomization, complete, has its appeal. It's easy to implement. It's not too bad, so maybe that. Randomized one at a time design, my favorite. Well, there's this problem. So if you're pretty sure that the probability of success is on both your treatments are higher than 0.5, you could well be comfortable with this because your startup is going to happen quickly. And perhaps overall, the permuted blocks is what one would be most comfortable with because it performed better than complete randomization and its features were very attractive, a little more attractive than the designs it represents. And of course, the experts in the beginning said complete randomization or possibly permuted blocks is the way to go. Now, this is the third apology actually, because in my abstract I said that I would give you some new results because there's another question that's now appearing, and that is how much does the startup procedure actually matter? What is the impact on the overall trial? And coupled with that, shouldn't we actually be looking at other startup strategies, the two that I've discussed, the fixed number of patients and just adjust, or possibly just take probability of success is to be a half and start the whole thing off straight away. And as I say, the bigger question and how one could actually compare what I've described with other startup strategies is to simulate full trials. You'd simulate with a variety of startup strategies, and you would also introduce the response-adaptive designs I mentioned earlier, the NAMAN, the acronym, and so on. Why haven't I done it? It's awful to say it, but I was all simulated out, and I just couldn't actually face another simulation for a while. If people think it's at all, I mean, I have a question here, if people think it's at all worthwhile, it probably is worthwhile to actually see what the impact is. Does it actually matter how we kickstart these designs? What do we gain if we do strategy number 1 up there with fixed numbers, or strategy number 2? And so that's the end of the talk. Thank you.
Thank you. So the talk is for discussion.
I could suggest another extension for you, which is actually finding out the best dose.
Sorry?
Finding out the best dose. If you had 4 treatment arms, then your probabilities would home in on the best dose. So often when you do a dose response study, you've got 3 doses,
yes,
which you want to pick to go into the next study.
Yes, I hear you. Yes, that's how I was all simulated out.
Yeah.
And there are sort of lots of questions. I took the simplest of all.
And that when you say maybe fixed, that you're always going to have placebo.
Yes.
And what you want is actually drop in the active doses. So at the end, you end up with the best dose being compared
Yes.
to the control, so you could go and show something. You said you wanted more extension. That's another extension.
Yes, yes, indeed.
Professor Rosenbaum.
Oh dear.
I came in a couple minutes late, so maybe you said this, but what kind of adjustment are you doing? Add 1 in the numerator and 2 in the denominator, or what do you recommend?
I'm slightly deaf. What did he say?
Well,
Let's tell her in German.
Say it again.
Sorry,
Bill.
it must be my American English. What kind of adjustment are you doing? Are you suggesting, like, add 1 in the numerator, 2 in the denominator?
Oh, for the fixed
Have you
number.
looked at different adjustments and seen?
I know. You actually told me about that, and there is a paper by
Maybe, is it aggressive?
you know who, Agresti and Kafka, I think. And there was a nice little thing you can fiddle with.
But did you look at different adjustments at all? Okay.
No, I didn't. I haven't really looked at either of those startup strategies. I felt they were better nested into a simulation of full trials.
Well, I
but-
kind of moved away from complete randomization and doing number 1. I'm doing 2 blocks of 6 and then the adjustment.
Yes.
1 in the numerator.
Okay.
Just wondering if you had,
I hadn't looked
if
at
you
it.
thought that
no.
was a good idea or not.
We were swimming in a wealth of results from simulations, and we stopped at that. Yes.
You especially said at some point that with a PA equal PB being 1/2 that you don't use Bayesian thinking here. What is the reason why you especially mentioned this? So why couldn't one use like something like a prior distribution or beta distribution?
I think you could. I actually think you could. I was assured that it probably wasn't Bayesian. You're giving each one a fair chance.
Yeah.
And that's it. But yeah, it's also a little arbitrary. And I wanted to keep Bayesian out of it because that's another whole set of simulations and results, yeah.
the problem might be where the Bayesian estimate is coming from. I mean, if you don't have any data and you start with the response-adaptive procedure, then okay.
Of course, the Bayesians always tell us that we frequentists go around with probabilities of a coin being throwing up heads is 0 or 1 is nonsense. Bayesian stats would tell you straight away that you mustn't deal with those sorts of things. The Bayesian paradigm is very tempting, actually. Yeah.
Okay, thank you very much for your